The last of the morning session, Lecheng Ren would tell us about symbol alphabets from tensor diagrams.
Thanks for the introduction, and thanks for organizing such a wonderful conference. So today I'm going to talk about some previous work with Mark and Natasha on the symbol alphabets from tensor diagrams. So as you have heard from Mark and Natasha's talk, that the loop amplitudes in E-equals Polytopes theory include these highly non-trivial transcendental functions. And one of the type of these functions are called multiple polylopes. And these functions are, these are functions of these so-called cluster X coordinates, which are cross ratios of the cluster variables in the G4N cluster algebra. And also one can use the symbols to study the structure of these multiple polylopes. And the symbol alphabets are then conjectured to be also these cluster X coordinates. However, only say so when there are 7 points and below, since the cluster algebras are finite, therefore we can indeed start with all these finite numbers of cluster variable and use the bootstrap programs by a group of elastics and to say bootstrap the symbol of very high parallel loop amplitudes only from these cluster variables, and by adding some other constraints like interpretability and some other physical constraints. But starting from 8 point, the cluster algebra here for G4N becomes infinite. Therefore, we need a truncation on these cluster algebra to reproduce the symbol alphabets in amplitudes, because since at each loop level, these amplitudes must be, say, a finite function, and in principle, there should be only finitely many symbol alphabets. So we want to look for some natural way in mathematics to reproduce these finite numbers of symbol alphabet at each loop level. So in this talk, I'm going to talk about some studies on patterns of these symbol alphabets. Okay. So here is the data computed by Songhee, Zhenjie Li, and Shi Zhang. Made some 2-loop and 3-loop 8-point amplitudes, and also some 2-loop 9-point amplitudes. So there are some very weird looking or very weird looking cluster variables. So if anyone can have some observation on these patterns, that would be very happy. Okay, so the tool I'm going to talk about here is called tropical Grassmannian. Say, since we are only interested in these cluster X coordinates, these cross ratios of cluster variables, we can parameterize these cluster coordinates by this representation of this GKN mod torus action. So mod torus just means we can locally rescale each column in this K by N matrix. And here we can just firstly take the first K by K matrix in this K by N matrix to be 1. And then the rest part, Mij, can be represented by this path from say like point I to point J, and sum over all the possible paths. And then for each path, we can take products of all the X variables below. So here the example of G3N, and we can have in general this prescription for any K. And then we can define a string canonical form on such GKN mod torus space, which is studied by Nima Song and also Thomas in the audience. So here, the omega is just the canonical form on this GKN mod torus, and this R factor is like the GKN generalization of the combination factors that appears in 3 amplitudes in physics. And then using the above parameterization, we can just parameterize all these I1 to IK plukers into these x variables and some f polynomials of these x variables. Okay, so how can these Grassmannian story help with the prediction with the simple alphabets? So remind that we need a finite set of these cluster variables. So if we tropicalize this RKN factor, we can get a G vector fan, say a finite G vector fan, in which in the whole G4 cluster algebra. And in the work by James Drummond, Jack Foster, Fomin-Pylyavskyy, and also Fomin-Pylyavskyy and 10K. For each G vector fan here, we can associate for each G vector here, we can associate a cluster variable. So for this finite G vector fan, we can then associate such a finite set of cluster variables. However, this process, when going to higher point, becomes highly cumbersome, since the cluster algebra for GKN just becomes very scary when the n grows. Therefore, we want to find some other ways to understanding this procedure, which can gives the connection between these G vectors and these finite set of cluster variables very naturally. Okay, and the story is to look at the dual of this G vector fan, which is the polytope, and here each boundaries can be noted by these kinematic functions as given here. Okay, so then the key things I'm going to talk about in this talk is the map between these finite set of cluster variables and these kinematic functions. And the way to understand this map is to regard these cluster variables by the object called tensor diagrams. Okay, so this is the basic structure of my talk. Any questions so far? Okay, so let's start from a simple example. Say for G35, the R vector, by parameterizing these generalized covariance factor, can be written in this way. And then when we tropicalize this R vector, the polytope we obtain is as follows. So there are 5 boundaries, and each boundary is due to this G vector. And finally, each G vector and each G vector here just corresponds to such boundary given here. And on the other hand, each G vector can also be associated to the cluster variables. So we need to find, so I want to just find a map between these cluster variables and these kinematic functions here. And then to study this map, we have to look at these objects associated to these cluster variables called tensor diagrams. So tensor diagrams is defined by Fomin-Pylyavskyy in 2016, saying that an endpoint SLK tensor diagrams is, say, a finite graph drawing inside a circle with n marked point along its boundary. And there are some conditions, say, firstly, say, all the boundary vertices have to be colored either black, have to be colored black, and can have arbitrary valence. So here, like each point here can be like valence 1 or valence 0, or here, they can also have valence 2. However, each internal vertex can be black or white, but each internal vertex must have only valence k. So here, this is 3 examples of SL4 tensor diagram. Say here that there are 4 lines, and here there are a double line and 2 single lines. So it's still valence k. So sorry, valence 4. And also each edge must connect a black and white vertex. And then for each tensor diagram, we can assign a function called invariant by assigning, say, for here, when we consider k equals to 4, so these functions in physics are just called the momentum twister. And then for each internal vertex, we associated such epsilon symbols, so which can contract each momentum twister's input. Okay, so here are the three examples. So this one is just a fluker of 1, 2, 3, 4, and this one is a more complicated one, which is a quadratic function of flukers. Say it's 1, 2, 3, 1, 2, 3, 4, 1, 4, 5, 1, 5, 6, 7, and then exchange the point 4 and 5. And here, there's another example where the 7 bar is just the combination of 3 points, say from 6, 7, and 8. And similarly, this 2 is also a combination of 3 points of 1, 2, and 3. Okay, and then from these tensor diagrams, a more important subset of these tensor diagrams is called web diagrams. And so far, here I only talk about k=4 web diagrams. Well, I think the study for higher k web diagram is still not really complete. And yeah, there are some other, I think there are some other tricky points that's not fully solved for higher k. So here I only talk about k=4. So the requirement is that each diagram should have at most double edges. So at most double edges and no triple edges. And there should be no 2 cycles. So it's like a reduced tensor diagrams. And then we can call it invariant. I call the invariant of each web diagrams as such a web invariant. Okay, so here the 3 examples we keep using are all just web diagrams. And also these SL4, all these SL4 tensor invariants satisfy the following skin relations, which is diagrammatically some diagrammatical identities, where if you apply these identities, the corresponding web invariants are unchanged. Okay. And also, we can classify web diagrams by arborizable or non-arborizable. Say, arborizable means that a diagram can be, through these sky relations, equivalent to another tensor diagrams without inner loops. So here, initially, we have such an inner loop. But applying the skin relations on these blue edges, we can identify this diagram with something like here. So here we have broken such inner loop. So it's now a tree tensor diagram. But here, for an example in SL3, and then also an example for SL4 tensor diagrams, web diagrams, these 2 web diagrams are not arborizable. So we cannot find any way using these scaling relations to break these inner loops and make it as a tree level tensor diagrams. Okay, and then so why we are interested in these tensor diagrams is because the conjecture in Fomin-Pylyavskyy is saying that each SLK endpoint arborizable web invariants are in 1-to-1 correspondence with these cluster variables or frozen variables in the GKN cluster algebra. So this is also proved up to 3.9 and also 4.8 by Fraser in 2017. So based on this conjecture, we can say that we then say that these cluster variables can be understood as these invariant of web diagrams. And then, so how to relate these web diagrams using that function to relate these web diagrams and the further kinematic functions on the, if you still remember, the polytope due to this G-vector fan. It's the next section. So the idea is, for each SL4 web diagram, we can associate a function of endpoints on P4. And for each configuration, we can associate the kinematic function as a linear combination of these generalized Mendelssohn variables, the SIJKL, where the coefficients of these Mendelssohn variables describe the level of coincidence of these 4 points in such configuration, right? For example, if we can have like a subset A of endpoints on P3, so saying that the points in A are coplane, therefore, say every 4 points. So since normally on P3, in general, we can only have 3 points coplane. And here is an extra coincidence saying that every 4 points now in this subset A can be coplane. Therefore, we define such a function saying that every 4 points, summing over these generalized maximum variables of every four points. And similarly, we can have a subset where points in the subset are all collinear. Therefore, here we use this square brackets to denote this collinearity. And therefore, each 4 points inside this subset are all collinear. Since collinear is in some sense higher than coplane, therefore we assign a higher coefficient 2 here. And also, for each, since the lines in the set B are all collinear, and if you have any point outside this subset B, then this extra point are always coplane with any 3 points on this subset B. Therefore, for any points outside this subset B, we can always have 3 points on the B that these 3 points and the extra points are also coplane. Therefore, we have an extra term denoting this property. And finally, we can also have points that collide, saying that all the points in this subset C are actually just 1 point. Therefore, for any 4 points in this subset C, in this collision is further higher than this collinearity, we assign a higher coefficient. And also, similarly, we can choose any point outside this subset C, which are collinear to the 3 points in this subset. So since they are collinear, we have this coefficient 2. And likewise, we can choose any 2 points outside this subset C, and choose 2 points on this in this C. And these 4 points, since C1 and C2 are colliding, these 4 points also share the same plane. So we also add such a term denoting their coplane, denoting that they are coplane. Okay. And then we define such map from web diagrams to the boundary configuration. It's this part. So since here every kinematic functions are associated with the boundaries of the polytope that I mentioned above, we can then call these configurations of these points on P4 as boundary configurations. So each boundary configurations denotes the relation between n points on this P4. Sorry, P3, sorry, on P3. And yes, and then each boundary configurations denote the relations of n points on P3. And for each configuration, we use these prescription to define the kinematic functions of generalized Manson variables. And then here's a definition of, say, starting from a web diagram to these boundary configurations, in other words, to these kinematic functions. For Plukers, we make such definition, say, for Plukers with A, B, C, D. So these 4 points, A, B, C, D, just denote how these points are arranged on such a plane. So we require points on, so we require firstly, there's a big plane. And then we have points from A+1 to B, all on this plane. And also we draw a line inside this plane where the points from B+1 to C are all on this line. And finally, there's a big point at the end of this line where points from C to D are all colliding on this, on this plane. So this is, say, a boundary configuration associated with such Pluker. And also for non-Plukers, there are also the corresponding, say, boundary configurations. And from the corresponding boundary configurations, we can define the associated kinematic functions. And in our paper, we can compute these further kinematic functions recursively. And this map is also appearing in series papers by Nick Early from some other context. Okay, so for example, at 6 or 7 and 7, 9 or 8 or 9 points, we can have for the following boundary configuration. Say we have 2 planes and there's some lines, and then finally on this line there are 3 points colliding, and also there's say a more complicated case, so also 2 planes, and there's a point colliding on the intersecting line of these 2 planes, and also on this plane we can have 2 extra lines. Okay. And also up to n points, up to 9 points, according to this this map from web diagrams to boundary configurations. So sorry, from web diagrams to cluster variables, we find these 5 different topologies on the symbol alphabet that appears in 8-point and 9-point amplitude computed so far. But we have to say that these symbol alphabets that predicted from the tropical Grassmannian is more than these those symbol alphabets appearing in actual loop amplitude. So actually, we need more prescriptions and more ideas on how to add on more constraints on such prescription to get the exact subset of cluster variables. So let me just summarize by such diagram. So here, firstly, we have the map between kinematic functions and the web diagrams and associated web invariants. So these are related by associate boundary configuration for each web diagram. And for each boundary configuration, there are kinematic functions. So here's the relation. And then for each kinematic function, well, we can it comes out from the tropical Grassmannian. So in this way, the tropical Grassmannian gives the predictions on the subset of web invariants that are conjectured to be the set of symbol alphabets appearing in loop amplitude. So that's it. Thank you.